Welcome, everybody. I'm Ethan Carlson, along with my teammates Aaron Scott, Brad Ratto, and Joe Johnson. We came together to complete our rocket modal analysis project. This project is comprised of the following four different parameters with their contributing constraints. Initially, we needed to design and prototype a launch vehicle to a scaled height of 2 feet through a CAD modeling software. We then need to send this over to the rapid prototyping lab to make our prototype into a material model. From here, we are tasked with finding the first 10 natural frequencies of our launch vehicle within the modal analysis toolbench in the software of our choice. Finally, we need to complete experimental structural dynamics testing using a modal hammer test and a shaker table test. Overall, our objective is to compare the simulated results with the experimental results and hope that they mimic each other as precisely as possible. My teammates will continue in more detail of each parameter, starting with prototyping.
So after a good deal of discussion about whether we should design a rocket from scratch, design a model based on a sci-fi rocket, or model a rocket after a real-life system, we landed on the consensus that modeling a real-life system would be best. We thought this might provide some interesting insight into scaled-down information regarding a real-life rocket and its resonant modes. So with that in mind, the rocket we ultimately selected was from the Soyuz family, which is a well-known class of expendable Soviet-era launch systems that were conceived around 1966 and that currently hold the title of the most frequently used launch vehicles in the world. So specifically, our team chose the Soyuz FG, which debuted in around 2001 and retired in around 2019 when it was replaced by the Soyuz 2. So we went with the Soyuz FG because it has a wonderful history and an iconic booster stage configuration. To design the model, we used SolidWorks in conjunction with the schematic shown a couple slides back. We scaled the schematic down such that the rocket height would be 2 feet according to our design constraints. Then we used the plane formed by the schematic to trace our one half of the rocket, then formed a body of revolution shown on the far left. After adding some payload stage features, we placed multiple sketch planes along the axis of a booster in the schematic and traced the tapering cross sections as we moved up that booster. We connected the cross sections with the loft tool, then circumferentially patterned the booster to form 4. Then the remaining details were added. We also modified the design to simplify for 3D printing. For most 3D prints, without using supports, a 45-degree overhang relative to the vertical is the maximum possible overhang before distortions are noticeable. So on the real Soyuz rocket, there are overhangs close to 60 degrees, so these geometries were constrained to 45 degrees as shown on the right. Also, the fins on the booster stage were removed and replaced with our required circular base plate. So now I'll hand it off to Brad to discuss our prototyping techniques.
Given the attention to detail that was considered when modeling the rocket, the team was able to use on-campus 3D printing facilities for our manufacturing needs. This allowed for quick turnover time, and which of course allows the ability to introduce design changes if necessary. The printer we selected was the Prusa Original. The material type we specified was a PLA plastic, white of course, which was printed using a 10% linear infill technique. The choice of using a 10% infill technique allows us again for a quick turnover time, but inevitably introduce discrepancies and differences between our response of our actual rocket piece and that of test sample data. This is despite using test sample data that was printed using the same infill techniques. This of course is due to the fact that when printing on 3D printers, the volume of infill is a function of its geometry and wall thickness. We will go into further detail in further slides denoting this deviation and any discrepancies we saw during testing and that of the modeling phase. As for the rocket itself, it was printed in 4 segments. This was done in order to maximize the overall assembled height of the model. However, this of course brings into question the method of assembly and any idiosyncrasies that may arise from having a non-singular print. In order to tackle the issue of assembly, the team decided to adhere a threaded rod within the top segment of the rocket, which would pass through the center hole of each piece. Given that the interface between the first 3 top pieces are concentric circles, there was no need to worry about the alignment due to the symmetrical nature of the pieces. However, the base and the penultimate piece, which sport the asparagus thrusters, required an alignment technique to be developed. For this, 4 steel dowels were adhered to the base to serve as an alignment pin at the interface of the 2 pieces. Once assembled, the rocket is placed under tension via an inset nut and washer at the bottom of the base. Overall, this assembly method gave the model a rigid feel and proved to be successful during testing. However, the threaded rod and the additional pieces used for assembly introduce other elements which contribute to the change in the overall response of the rocket under the force oscillatory test. Further discussion of these techniques in order to model these effects and the deviations due to the manufacturing process will be discussed in upcoming slides.
So the goal for our modal analysis is to locate the primary resonant frequencies for our model and their associated mode shapes. We performed numerical simulations in the SOLIDWORKS simulation toolbench, where a sine sweep was iterated to locate the first 10 modes. The animation on the right shows the first mode shape as an example. The legend shows the magnitude of the displacement response, which would scale relative to the magnitude of the input. To set up the analysis, we applied a fixed boundary condition to the base of the rocket, and all component contacts were set as perfectly bonded. We used standard 3D models for our mounting hardware from McMaster-Carr for the closest relevance to our real-world prototype hardware. There weren't any geometrical simplifications to our simulated model, aside from excluding the bolt threads from the model to improve the simulation performance. The material properties for all the components in the numerical model are listed in the table on this slide. The steel components used SOLIDWORKS plain carbon steel material profile for the mounting hardware, and the material properties for the 10% infill PLA came from experimental data in the Experimental Space Systems Lab. Finally, we performed a mesh refinement study to ensure that the results of the simulation were not dependent on mesh size. We tested multiple incremental refinements between these 4 images and ultimately settled on mesh C. Our simulation results show natural frequencies at approximately 66, 308, 524, 656, 718, and 1250 Hz respectively. The natural frequencies that show up in pairs are bending modes, and the reason they show up in pairs is that it's effectively the same mode shape but acting over 2 different perpendicular axes. So the exception is mode 7, which is a torsional mode, and mode 10, whose pair is actually mode 11, which isn't listed. Here we see animations of the bending modes and the single torsional mode 7. Modes 1 through 4 and 8 through 10 show relatively typical beam bending behavior, whereas modes 5 and 6 show isolated bending occurring in the Soyuz's System 4 Emergency Rescue Module. So to verify our simulation results, I'll hand it off to Joe, who will be covering the structural dynamics testing portion of our presentation.
Structural dynamics testing is used to ensure that a structure can support subsystems and payloads in order to prevent any failures that could lead to an unsuccessful mission. It ensures that a spacecraft can handle the mechanical loads that are put on it during transportation, launch, and flight operations. For our testing, the Soyuz prototype was fixed at the base by screwing it to a shaker table. During our analysis, we used the shaker table to perform a sine sweep test in order to determine the model's natural frequencies. A modal hammer test was then performed, also to determine the model's natural frequencies. This test was performed with 4 different sensor placements, which will be shown in the following result slides. When the shaker table test was completed, the compiled data was already in the form of time and frequency, so we simply plotted the frequency versus the time, and the resulting high peaks represented the natural bending mode frequencies. When the modal hammer tests were conducted and the data was compiled, it was given in the form of time and acceleration. So with the shown MATLAB code, we utilized a fast Fourier transfer to obtain the frequency versus time plot, and just like the sine sweep test, we selected the proper corresponding natural bending mode frequencies. It is difficult to see from the picture, but for this test, the sensor was placed near the top of the rocket and aligned with the lower pylons. After performing a modal hammer test 3 times and averaging the modes, their associated frequencies are as follows. For mode 1, in Hertz, the average frequency was 43.4. Mode 3, 216.9. Mode 5, 400.6. Mode 8, 513.9, and Mode 10, 833.5. In the table, you can see that there is no value for Mode 7. When the experimental data was analyzed, a corresponding mode cannot be found. Our assumption was that this is likely because Mode 7 is a torsional mode and thus has a low magnitude in comparison to the bending modes. For this test, the sensor was placed near the base of the rocket and once again aligned with the lower pylons. The average frequencies found from 3 modal hammer tests are as follows: Mode 1, 44.9, Mode 3, 213.1, Mode 5, 400.6, for Mode 8, 519.4, and for Mode 10, 844.2. For this test, the sensor was once again placed near the top of the rocket, but this time the orientation was changed so the sensor was positioned between 2 pylons. The average results of 3 more modal hammer tests were as follows: for Mode 1, 42.5, for Mode 3, 210, for Mode 5, 402.8, for Mode 8, 508.95, for Mode 10, 866.4. For our final test, the sensor was once again aligned between 2 pylons, but placed closer to the base of the rocket. The average natural frequencies found are as follows: for Mode 1, 44.2, for Mode 3, 210, for Mode 5, 392.6, for Mode 8, 523.8, and for Mode 10, 831.9. To find values for comparison to the theoretical values that were found using SolidWorks simulations, the results of each modal hammer test and sine sweep test were all averaged to obtain the following natural frequency values: for Mode 1, 44.6, for Mode 3, 215.2, Mode 5, 400, for Mode 8, 520, and for Mode 10, 844.99. When the experimental results are compared to the simulated values, an obvious discrepancy is noticed, but when calculating the percentage difference between the modes' associated frequency values, the percentage difference appears to be relatively consistent from mode to mode. Averaging these percentages shows an average percentage difference of 41.55 between the experimental values and the simulated values. This correlation issue is likely due to an error in material properties used for the simulations, and the error in material properties is likely due to the prototyping process, 3D printing patterns, and/or discrepancies in the printing infill percentages.
As mentioned previously, we have a consistent difference percentage from the theoretical results to the experimental results. Consequently, we did complete the objective of simulating, testing, and analyzing our launch vehicle to a very close degree. However, when comparing results, we found out that due to unforeseen issues, these values did not correlate directly. Our most outstanding findings may be the cause of this correlation, as we found that even if the infill percentage remains constant, the internal geometry can have a big impact on the material's behavior. Although our team has some previous preliminary experience in various aspects of the project, we all either gained new experience or advanced our existing experience in prototyping, animating, finite modal analysis, and the simulation and experimentation processes. Thank you for your time, and we are happy to answer any questions you may have.